All right. Hello, everyone, and welcome to today's episode of Breakout Mentors Machine Learning. Today, we've got a good one for you. My name is Kai. I am the Director of Machine Learning at Breakout Mentors. And today, we're going to be covering a few things. So, one second, let me share my screen so you guys can all see what I'm looking at too. Cool. Awesome. So, in today's episode, we're going to do a few things. We're going to fit a linear regression model to understand the relationship between ad spend and iPhone sales. Then we're going to connect statistics to machine learning and talk a little bit about how they're related and how they're different. And then we're going to wrap up by describing how you can start learning machine learning and building machine learning powered apps. So cool. With that, let's get rolling. Cool. So, and by the way, the platform I'm using to write this code and share this episode is on Google Colab. Cool. All right. So the first thing we're going to do is linear regression, right? So Apple is preparing to launch their new iPhone 14, and they need help determining whether they should invest in running an ad campaign for the new iPhone. They also need to know if they decide to run that ad campaign, how much should they spend on that campaign and how much can they expect basically to get back in terms of the number of iPhone units that they sell. So cool. So our task is to use the historical sales data that Apple has given us to determine whether there is a linear relationship between ad spend and iPhone sales, and then to predict the number of iPhone units that they will sell given the amount they want to spend on advertising. So the approach we're going to take, right, is we're going to fit a regression model to the data, and then we're going to use the model to perform a hypothesis test and make predictions. Cool. All right. So the first step in any linear regression, right, is to load the data. So we're going to use Python. This is what I'm using up here, right? We're using Python, we're importing some libraries and things like that. And the first step in our linear regression analysis is we need to load in our data. So we have the Apple historical sales and ad spend data here, and we load it up, and we can see that there are 200 rows and 2 columns, right? And the 2 columns are, the first one is called ad spend, and the second is sales. So here's a little write-up about what these 2 columns represent. So ad spend represents the amount of money spent on advertising in millions, and sales represents the number of iPhone units sold in millions for a given ad campaign, right? So now the important thing that we need to establish is what is going to be our explanatory variable and what is going to be our response variable, right? So in this case, right, we're trying to predict whether, to determine whether ad spend explains iPhone sales, right? So in that case, ad spend is going to be our explanatory variable, and sales is going to be our response variable. Cool. Now, the next thing we need to do in a linear regression is to check our conditions, right? And all of you who have taken or are in AP statistics will be very familiar with these conditions, or at least you should be. So the first one is we got to make sure that our variables are quantitative, right? And we see from our data up here that that condition has already been met, which is a good thing. And the next, now there are 3 other conditions we need to meet, right? So we need to make sure our data is linear. Does it even make sense to fit a linear model to this data? We're going to need to check for outliers. And if you recall, that's important because outliers will affect our means, and they'll affect the way that how much we can trust our linear model. Excuse me. And then the last thing we need to check is our equal variance condition. So, are there any patterns, obvious patterns in our residual plot? Do they look relatively normal, normally distributed, things like that. So we need to make sure that the residuals show no patterns and that they're equally spread across the positive and negative around 0. So cool. So the first step to meeting these conditions is let's plot our data. So we're going to take our data and say that the X column is ad spend and the Y column is sales. And then let's take a look. Cool. So now we can see our data here. Ad spend again is on our X axis, and Y, it has our sales. And here's the scatter plot, and we can see, let's take a look. And to me, this looks pretty much like we could fit a linear model to it. It looks like the relationship is relatively linear, and I feel pretty confident that we will be safe fitting a linear model here. So with that, we can see that we've met the straight enough condition. Now for the outlier condition, I see that there is a cluster around between 240 and 350 almost, it looks like, that kind of pulls this down. So it might pull our mean down for Y a little bit, but it doesn't look too bad. I think I feel confident that this is okay. And, this is representative of real world situations. You're never going to have a perfectly linear thing. So yeah, I feel pretty good about this. So now the last condition we need to meet is the equal variance condition. And again, in order to meet that, we need to fit a regression model and take a look at the residual plot. So let's do that next. All right. So in order to fit a linear regression model to our data, we're going to use the following Python code. So we're using the stats models package, and we're going to define an ordinary least squares regression line, which is, again, a linear regression model. And we're going to define the relationship we're trying to fit. So we're going to, our response variable, our Y variable, is sales. And our explanatory variable here is ad spend, right? That's our X. So that's our input, right? So we've defined the relationship we're trying to model. We're passing in the data, and we're fitting the linear regression model. So then we make predictions. We're going to store those in our data frame, which is this thing right here. So we're going to store those predictions, and then we're going to measure the residuals, and now we're going to plot it. And again, don't worry too much if you don't recognize or understand what this code is doing. I'm just showing it to you for brevity. But yeah, so now let's plot it and visualize the fitted model and the residual plot to make sure all of our conditions are met, and we can decide. So taking a look at the line of best fit, yeah, it looks like we fit the data pretty good. I mean, the values above the line and below the line look relatively equally distributed, which would be one way of verifying the equal variance. But again, the best way is to really look at this residuals plot, and taking a look here, we can see that it looks relatively random, no obvious patterns in the data. This is a little concerning, like we said, but we kind of expected that already, and it seems to level out. I guess one argument you could maybe make against this is that as X increases in value, right, as ad spend increases, the variance increases. But for now, let's say that this is pretty good. I feel confident about it. So yeah, so we've met all of our conditions, and we're ready to analyze the relationship between ad spend and iPhone sales using our linear regression model. So cool, let's interpret the model now. Here we're going to print out some descriptive statistics about our model, and then interpret them. Okay, so this printout, we can see a few things. Don't worry, All we really need to pay attention to and understand is this, right? We want to understand this R squared value. And that is the coefficient of determination, as you might know and recognize. Here we can see the fitted values for the y-intercept and our beta 1 value, or our slope here. And then their standard deviation, their t values, and their two-sided t-test, the p-value from a two-sided t-test, and then the 95% confidence interval for each of these variables. Cool. So interpreting these results, let's take a look. The equation for our least squares regression line is sales. The predicted number of sales is equivalent to 4.243 plus 0.0487 times ad spend, right? So in statistics, we always want to interpret this in context, and in general, whatever field you're in, you always want to contextualize the data. So the y-intercept in this case represents is 4.243 represents the predicted number of iPhone units sold in millions when Apple spends $0 on advertising. So that's kind of interesting. I mean, maybe, you know, Apple is so big now and so well known that even if they didn't spend any dollars on advertising, they would still probably sell about 4.2 million iPhones. So, and then interpreting the slope in context, we would say for every additional $1 million spent on advertising, the number of iPhone units sold is expected to increase by approximately 48,760. So now moving on to the correlation coefficient, which we see here, it's 0.868, and interpreting this with a value of 0.86, this indicates that there's a strong positive linear relationship between ad spend and the number of iPhone units sold. Interpreting the coefficient of determination, right, which measures the amount of variance that we can explain, can be explained from the linear model, right? So approximately 75.2% of the variability in iPhone sales can be explained by a linear relationship between the ad spend and the number of iPhone units sold. Cool. So now that we have pretty much determined that a linear regression model is appropriate, all of our conditions have been met, and we've interpreted the output of our model, let's run a hypothesis test to determine whether ad spend influences iPhone sales. Cool. So first, let's establish our hypothesis, which the null hypothesis in this case would be beta 1, or our slope, is equal to 0, right? So there's no evidence that there's a linear relationship between ad spend and iPhone sales, i.e. Ad spend does not influence iPhone sales. And then our alternative hypothesis is going to be that the slope does not equal 0. And in this case, we would maybe interpret this as an indication that there is, one, a linear relationship between ad spend and iPhone sales, and two, that ad spend does influence the number of iPhone units sold. Cool. So let's take a look again at our model statistics, the printout summarizing it. And we can see a few things. Like I mentioned before, we can see our p-values for a two-sided t-test at an alpha of 0.05, so 95% confidence, right? And interpreting this p-value and determining whether we reject or accept, or excuse me, whether we fail to reject the null, or if we reject the null. Looking at the p-value for our slope, we can see that it's reported to be 0.00 to the fourth decimal. And this is significantly smaller than any typical significance level. Or well, I guess I should say, I should be careful with saying that it's significantly smaller, because this is statistics, right? But it is much smaller than any typical significance level in statistics. And as such, we would reject the null hypothesis that that ad spend does not have any influence on iPhone sales. And we would conclude that iPhone sales are significantly influenced by ad spend, i.e. we rejected the null and going to conclude that iPhone sales are significantly influenced by ad spend. Now, something interesting is Apple is probably less interested in whether there's any relationship between ad spend and iPhone sales. They probably want to know if there's a positive relationship between ad spend and iPhone sales. Like, in other words, does ad spend positively influence iPhone sales? So in that case, our alternative hypothesis would change from the slope is not equal to 0 to the slope is greater than 0. And in order to test that, we can take the p-value from our two-sided t-test, which is shown here, right, again, and divide it by 2. So dividing 0 by 2 is still 0, and we'll reach a similar conclusion. So we reject the null hypothesis that our slope is 0 and conclude that ad spend has a significant positive influence on iPhone sales. So pretty interesting, right? Now, we may eventually want to get the 95% confidence interval for our slope using this this alternative hypothesis where we're looking at does ad spend positively influence iPhone sales? So in that case, we're going to use a right-tailed, in other words, a one-sided right-tailed t-test. And we're going to take a look at these values. So let's interpret this 95% confidence interval. We can be 95% confident, right, that the mean number of iPhone units sold increases between 45.4 thousand and 52,000 for every $1 million that Apple spends on advertising. Now, something important is it's now up to Apple's management to decide whether or not they want to actually spend more on advertising based on these numbers. In other words, do the sales numbers increase significantly enough for them in a business sense to justify spending more on advertising? But that's a question we leave for Apple's management. Now, moving on to the final step of our linear regression, we're going to predict the number of iPhones sold when the money spent on advertising is 450 million. So when Apple wants to spend 450 million on advertising, and they want to have some idea of how much or how many iPhones they can expect to sell as a result. So plugging it in, we look again back at our linear regression equation, and we get this equation here, and we plug in our values. So the resulting value is 26.158. So approximately 26 million units are expected to sell if Apple spends 450 million on advertising, right? So now a bonus challenge for you is to determine what the 95% confidence interval for the expected number of iPhones sold when Apple spends 450 million on advertising is, right? So if you remember, you're going to need to calculate some of this, something similar to what we did up here with these confidence intervals for the intercept and the slope, and then do a few more mathematical manipulations to get that value, but I don't want to give the answer away. So cool. So now let's plot the line of best fit. Let's plot our prediction that we made for the 450 million spent on advertising. And then let's also plot our 95% confidence interval for the line of best fit. So to do that, we're gonna first plot the scatter plot like we did before. Then we're gonna add our line of best fit. And then we're gonna make our prediction, which we're doing here, passing it into our model and producing our y hat value. And then we're gonna plot that point and then add our confidence intervals here. Cool, and let's take a look. And boom, that's what we get. So taking a look, as we expected, right? So as X is smaller, the confidence interval seems a little bit tighter and more concentrated around the line of best fit. And then as X gets larger, the confidence interval begins to spread, right? It begins to spread more. Cool. And then taking a look at our predicted point, we see that if Apple spends 450 million, they can expect to sell approximately 26.15 million iPhone units. So pretty cool. Awesome. So yeah, so now we've answered our first problem that we set out to do in this episode, which is to fit a linear regression to a problem. In this case, we fit a linear regression to Apple sales data and ad spend. And what we learned is that ad spend does significantly influence, or we failed to reject the null. We rejected the null, and we conclude that ad spend has a significant positive influence on the number of iPhone units sold. And we left it to Apple's management to determine whether the amount of units sold is significant enough for them to invest more in ad spend. All right, so now moving on, let's connect statistics to this very exciting field that you might have heard a little bit about recently called machine learning. So machine learning and statistics have a lot in common, and they share many traits and characteristics. But machine learning is special in the sense that it's kind of it's a combination of computer science, statistics, and math. So it combines elements from all three and produces, something like this, right? Silly little meme, but yeah, machine learning, the primary difference between machine learning and math and statistics and things like that is machine learning is very focused on maximizing the predictive power that it has. So it's very focused on practical business applications compared to like statistics or math, which do have practical applications, as you've seen in your AP stats class, maybe. But machine learning focuses more on the business use cases, while stats and math focus a little bit more on explanatory power. So like understanding a relationship between data and explaining and meeting theoretical constraints. While machine learning, they just really want to make good predictions about the data. So let's talk a little bit about the strengths of machine learning. So machine learning can handle nonlinear data, right? So if our data couldn't be fit by a linear model, that's not a problem for machine learning. There's algorithms that can handle that, no problem. It can handle multivariable data, so more than one explanatory variable. It can handle hundreds, thousands, even millions of explanatory variables. It can handle tons of data, and it can handle. It's able to model complex and multi-domain data, so it can model and learn relationships from text. It can learn and model picture data, videos, audio, and combinations of all these. So it's very impressive. It can model very complex and kind of ambiguous data. And another exciting thing is it's able to improve over time. So the more data it's fed, the better the models become, which is, again, in some ways similar to statistics, where the larger your n value, right, the better and more confident you can be about your model fit. And then the last thing that's very unique to machine learning is it's able to enhance human experiences. So I'll show a few examples of what I mean by this, but it's machine learning paired with humans is able to make, as we can see here, a happy human. So it's able to augment your learning experience. It's able to help you be more creative. It's able to help you level up your skills and be more productive. So a couple examples to give you context of exciting machine learning applications. Here's one showcasing how machine learning augments learning and productivity, where there's an ML application that assists you in programming. So here, a programmer might not know how to program in this specific language. So what they do is they type out they type out in words what they want the program to achieve. And the machine learning model will read this comment that they typed out and generate code for them, which is pretty incredible and very powerful. In fact, this specific example, this machine learning algorithm is able to generate entire video games just from text descriptions, which in code, which is awesome. Okay, so another really exciting example of machine learning is machine learning for creativity, where the machine learning algorithm is able to generate images from human text descriptions. So humans input some text and the machine learning model generates images from that. So let's take a look at two cases that I found kind of funny and cool and interesting and beautiful. Here, the text input was chai waterfalls in various art styles and environments. And I don't know about you, but I find these quite impressive. And there's lots of variation and very unique types of art here, and it's very creative, which is really cool to express and has lots of potential. And then another fun, a little bit more of a fun one here, a silly one, is a text input where we say Darth Vader at a tech conference. So, for all those Star Wars fans, this is what Darth Vader might look like if he had to go to a tech conference. And you can see that the machine learning model is actually able to, it picked up that not only is Darth Vader Star Wars, but it even draws and adds some additional Star Wars characters to these images without us even prompting it to do so, which is really cool. Awesome. And then another very practical and exciting area of machine learning powered applications is for safety and health. So machine learning for object recognition and disease detection. Taking a look at some of the cases and examples here, we see for like object detection, with self-driving cars, machine learning algorithm is able to use sensors and cameras on the car and determine what is in front. So it's able to identify the positioning and the type of object that's in front of it. It sees that there are several cars in front of it. There's a bus over there, right? And then on this other example, machine learning model sees a dog, a person, and a horse all in front of it, which is pretty awesome. And then for health and safety, there's another example where the machine learning model is given x-rays of potential pneumonia patients, and it helps doctors better diagnose patients and give them the correct diagnosis. So the machine learning model looks at the chest x-ray and shows the doctor where it has detected pneumonia in this patient, and the doctor reviews it and has a better sense of what might be going wrong and what type of diagnosis to give that patient. And another exciting one is with brain tumors. So using MRI data, the machine learning model takes a look at the brain scan and can find where in the brain it found a tumor, and then it also is able to segment the different sections of that tumor in the brain for the doctors, which is really important for when they're, maybe needing to do an operation or detect and understand what type of tumor it is, and things like that. So lots of really exciting application areas here. Now, now that you've seen a few, examples of machine learning and the powerful applications you can build with it, how would you get started learning machine learning and building machine learning apps? Well, there really are only 4 steps, and 2 of them you've already completed. So it's recommended that you learn the foundations of statistics, which you've already done if you've completed AP stats. And then the next thing you're going to need is to pick a coding environment. So the coding environment I'm using here is Google Colab. So you've already completed 2 of the 4 steps. And then the last 2 are very important. So choosing a learning resource. You can learn from a book, a large online open course, a university course, or use more of a personalized approach where you get a personalized curriculum and you have a mentor who kind of walks you through the field and helps guide you and things like that. And then once you've chosen your learning resource, you just get to it. So you start learning and building. And this is very important. So like whatever resource you choose, you got to start and you got to try building. That's the only way these things will stick, as you probably learned in your stats class. So in my opinion, and in my experience working with a number of people and also myself and my friends, the best and most enjoyable way to learn machine learning is by doing interactive lessons, building projects that interest you, and having a mentor that supports you along the way, right? So Breakout Mentors, we provide our machine learning students with highly personalized one-on-one mentorship, interactive lessons, and hands-on project support. Everything from brainstorming your machine learning projects like these to implementation, like how to implement them, and then how to share them with the world. So we help you end to end. And when the students who complete our program, they come out having an intuitive understanding of the foundations of machine learning. They're able to think like a data scientist and build impressive real world machine learning projects, from web apps to research publications, regardless of their background. So we have students who come from, they bring in advanced math knowledge and programming knowledge, and some machine learning knowledge maybe, and they do really well. But we've also had, but the majority of our students come in with very little math knowledge, very little programming knowledge, and no or very little machine learning knowledge. And all of these types of students are able to succeed in our program. We have a track record of students in our program winning awards at local and national competitions for the ML projects we've helped them build. They've landed internships in industry and academia, and they've also received admission to some of the top universities in the world, all from, showcasing projects and building out their skills and things like that. So it's very exciting. So, if we're not the only way to learn, but I would like to think that we are one of the best, if not the best way to learn, especially if you're in high school or middle school. But particularly for high school students, we have a really strong program, a really good track record, and we offer a lot of cool options for you. So we have summer intensive programs where you meet with one of our mentors one-on-one on a schedule that works with you. And then we also have long-term learning over the school year where you meet once a week or once every 2 weeks with a mentor. and you'll go through the machine learning foundations and learn everything you need to know to be able to build machine learning applications from scratch. And then we also help you with projects. So if you're interested, you can reach out to me. You can schedule a phone call with me by going to breakoutmentors.com/Kai, Kai. You can read more about our machine learning program by going to breakoutmentors.com/ML, or you can send me an email at you can send me an email at kai@breakoutmentors.com, and I'll get back to you. But yeah, so that's the end of the lesson today. We covered, as we spoke about a little bit earlier, we covered linear regression. We used Apple sales data and ad spend. We then covered and connected how statistics is related to machine learning and how they complement each other. And then we also took a look at what machine learning excels at and how you can get started learning it. So I hope you enjoyed today's episode and hope to see you soon.